Tonight, we're going to follow the loneliest object humanity has ever created. Not lonely in a poetic sense. Lonely in the most literal, physical sense possible. An object that is right now, at this exact moment as you watch this, farther from Earth than anything we have ever built. Farther from the sun than any human-made object in history. Traveling through a region of space that no spacecraft has ever entered before, in a direction that will take it away from everything it has ever known, forever. Voyager 1 is a spacecraft the size of a small car, weighing about 721 kilograms, launched in September 1977 from Cape Canaveral, Florida. It carries instruments built with 1970s technology. Computing power roughly equivalent to a cheap pocket calculator by modern standards. It is powered by 3 radioisotope thermoelectric generators that convert the heat from decaying plutonium-238 into electricity, generating less power than a dim light bulb. And it is the farthest traveled object in human history. The most distant artifact of our civilization. The only thing we have ever made that has left the solar system entirely and entered the space between the stars. Tonight, we're going to follow Voyager 1 through its entire journey. From its launch in 1977, through its flybys of Jupiter and Saturn, through the discoveries it made that permanently changed our understanding of the outer solar system, through its crossing of the heliopause and entry into interstellar space, to where it is right now, still transmitting, still alive, still sending data back from beyond the edge of the solar system. And then we're going to follow it forward, 10,000 years from now, 100,000 years, 1,000,000 years, 1,000,000,000 years, to understand where it's going and what it will encounter on a journey that will never end. Because Voyager 1 will never stop. It will never be retrieved. It will never return. It is on a trajectory that takes it away from the sun forever, into the vast dark between the stars, for as long as the universe exists. That is what tonight is about. By the end of this, you're going to understand what Voyager 1 has seen, what it has taught us, what it carries, and what will happen to it across timescales that make human history seem like a rounding error. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand Voyager 1, you have to understand the world that built it. The specific moment in history when a civilization decided to send a piece of itself into the permanent dark. It was 1972. Richard Nixon was in the White House. The Apollo program was winding down. The last humans to walk on the moon, the crew of Apollo 17, would do so in December of that year. The Vietnam War was still ongoing. The Cold War between the United States and Soviet Union was shaping every major decision in science, technology, and space exploration. And a small group of engineers and scientists at the Jet Propulsion Laboratory in Pasadena, California, were working on something that had never been attempted before. They had identified a rare planetary alignment, a configuration in which Jupiter, Saturn, Uranus, and Neptune would be positioned in a rough arc on the same side of the Sun, making it possible for a spacecraft to visit all 4 in a single mission using gravitational assists. This alignment occurs only once every 175 years. The next window would be in the late 1970s. The mission that would eventually become Voyager began as something far more ambitious, a grand tour of all 4 outer planets, conceived in the late 1960s. Budget constraints eventually reduced it. NASA approved a more modest version, 2 spacecraft, each capable of visiting Jupiter and Saturn, with one potentially continuing to Uranus and Neptune if it survived. The 2 spacecraft, Voyager 1 and Voyager 2, were built by the Jet Propulsion Laboratory. They were identical in design, though their trajectories would diverge significantly. Voyager 2 was launched first, on August 20th, 1977. Voyager 1, despite its name, launched second, on September 5th, 1977, but on a faster trajectory that would allow it to reach Jupiter first. The spacecraft design reflected the engineering philosophy of the era. Redundant systems, robust construction, carefully managed power budgets. The computers on board had a combined memory of about 68 kilobytes. A single modern smartphone has roughly 1,000,000 times more storage. The radio transmitter broadcast at 23 watts, roughly the power of a refrigerator light. That 23-watt signal, by the time it reaches Earth from Voyager's current distance, arrives with a power of approximately 10 to the minus 16 watts, 10 million billion times weaker than what was transmitted. Detecting it requires the most sensitive radio receivers ever built. The cameras on Voyager were Vidicon tube cameras, technology essentially derived from television cameras of the era. The images they produced were transmitted back to Earth in digital form, each image taking hours to receive at the data rates available across planetary distances. The entire imaging system, by modern standards, was primitive. And yet, what it would capture would be extraordinary. Before we follow Voyager on its journey, we need to talk about what it carries. Because Voyager 1 is not just a scientific instrument, it is also a message from humanity to anyone or anything that might ever find it. On the outside of each Voyager spacecraft is mounted a 12-inch gold-plated copper disc, the Voyager Golden Record. It was conceived and produced under the direction of astronomer Carl Sagan, who assembled a committee of scientists, artists, and thinkers to determine what humanity would say to the universe if given the chance. The Golden Record is not a simple greeting. It is a comprehensive portrait of life on Earth and of humanity's place in the cosmos, encoded in a format designed to be decipherable by any sufficiently advanced technological civilization that might find it. The disc contains 116 images, encoded in analog form. Photographs of Earth's landscapes, its life forms, its people, its science. Mathematical diagrams, anatomical illustrations, photographs of humans in different cultural contexts, a family, a mother nursing a child, an athlete in competition. Photographs of the natural world, mountains, oceans, deserts, forests, the solar system, DNA structure, human anatomy. The disc contains greetings from the people of Earth in 55 languages, ranging from Akkadian, an ancient Mesopotamian language no longer spoken, to Wu, a Chinese dialect. The United Nations Secretary-General Kurt Waldheim contributed a greeting. Children's voices were included. The sounds of different human languages were arranged to give any listener a sense of the diversity of human speech. The disc contains 90 minutes of music from around the world. Bach's Brandenburg Concerto No. 2, Mozart's The Magic Flute, Beethoven's Fifth Symphony, specifically the Cavatina from String Quartet No. 13, Chuck Berry's Johnny B. Good, Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a Pygmy Girl's initiation song from Zaire, a Navajo night chant, a Peruvian wedding song, Azerbaijani bagpipes, an Australian Aboriginal song, Indian classical music, Japanese shakuhachi, Georgian choral music, the sounds of different musical traditions from around the world, selected to represent the full diversity of human musical expression. The disc contains sounds of earth, the sound of rain, of surf, of wind, the sounds of animals, birds, whales, chimpanzees, frogs, the sound of a heartbeat, footsteps, laughter, a mother's first words to a newborn, the sound of a fire burning, Morse code, a pulsar, volcanoes, earthquakes, the sound of Earth itself. On the cover of the record, engraved in gold, is a diagram explaining how to play it, the correct speed, the stylus angle, the expected output waveform. There is also a diagram of a hydrogen atom, the most common element in the universe, used as a time standard, and a pulsar map, a diagram showing the position of the Sun relative to 14 known pulsars, each identified by its unique period, which could be used by any finder to identify exactly where in the galaxy the record came from. This pulsar map is perhaps the most profound element. Carl Sagan and his colleagues essentially created a map that says, "This is where we live. This is where you can find us. These are the unique identifiers of our location in the galaxy, expressed in a physical language, the timing of pulsars, that any sufficiently advanced civilization would be able to read. Whether anyone will ever find the golden record is essentially impossible to calculate. Voyager's trajectory does not aim it at any specific star. It will drift through interstellar space for an almost incomprehensible amount of time before coming close to any other star system. The probability that any civilization will encounter it in any foreseeable time frame is vanishingly small. But that isn't really the point. The golden record is less a message to extraterrestrial intelligence than it is a statement of what we are, a species that, in the midst of the Cold War, the Vietnam War, and all the chaos and violence of the late 20th century, chose to put Bach and whale songs and a mother's first words to her child on a gold disc and send it to the stars. Carl Sagan wrote about the golden record. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Voyager 1 crossed the asteroid belt without incident. The asteroid belt, despite its dramatic reputation, is largely empty space, and the probability of a spacecraft being hit by an asteroid while crossing it is very low. And on March 5, 1979, it made its closest approach to Jupiter. Nothing could have fully prepared the scientists at JPL for what they saw. Jupiter was not unknown before Voyager. Pioneer 10 and Pioneer 11 had made brief flybys in 1973 and 1974, returning some images and data. But the quality of those images and the brevity of the encounters had left Jupiter largely mysterious. Voyager 1 would spend months approaching Jupiter, returning thousands of images as it drew closer, and then make a close approach that would reveal the planet in extraordinary detail. The Great Red Spot, Jupiter's famous storm system, which had been observed from Earth for centuries, was revealed in its full complexity for the first time. It's not simply a red oval. It's a hurricane 3 times the diameter of Earth, with internal wind speeds of hundreds of kilometers per hour, with a structure that changes over weeks and months in ways visible in Voyager's images. Watching the time-lapse movies assembled from Voyager's images of Jupiter's cloud tops, the swirling bands, the turbulent eddies, the complex interactions between different atmospheric features was, for the scientists watching, like seeing a living system for the first time. Jupiter's atmosphere was revealed to be extraordinarily dynamic. The banded structure visible from Earth, the alternating light zones and dark belts, was understood to be driven by east-west jet streams moving in opposite directions, with complex interactions at the boundaries between bands creating swirling eddies and storms. Lightning was detected in Jupiter's atmosphere. Enormous lightning bolts, far more powerful than anything on Earth. But the most stunning discovery wasn't Jupiter itself. It was what Voyager 1 found around it. On Io. Io is Jupiter's innermost large moon, one of the 4 Galilean moons first observed by Galileo in 1610. Before Voyager, astronomers knew Io existed, knew roughly its size, knew it had an unusual reddish-orange color. They didn't know why. When Voyager 1's cameras resolved Io's surface in detail for the first time, the scientists were astonished. Io's surface looked like nothing ever seen in the solar system. It was covered in complex terrain, plains, mountains, calderas, in extraordinary colors: orange, yellow, white, red, brown, black. There were no impact craters visible anywhere, which was deeply strange. Every other solid body in the solar system that had been imaged showed impact craters, the accumulated record of billions of years of bombardment by asteroids and comets. Io had none. The reason became clear when navigation engineer Linda Morabito, processing Voyager 1 images 8 days after the flyby, noticed something anomalous in a photograph taken for navigation purposes. There was an umbrella-shaped plume rising from Io's surface, a volcanic eruption captured in the act. Io was volcanically active, extraordinarily active, far more active than Earth. The surface was being continuously resurfaced by lava flows and volcanic deposits, which explained why there were no impact craters. They were being covered over almost as fast as they formed. 9 active volcanoes were eventually identified in Voyager 1's images. Eruption plumes rising hundreds of kilometers above the surface. Lava flows spreading across the landscape. The energy source for all this activity was identified: tidal heating. Io is in a gravitational resonance with 2 other Galilean moons, Europa and Ganymede, that keeps its orbit slightly elliptical. Jupiter's immense gravity flexes Io as it orbits, generating heat in the interior through friction. That heat drives the most volcanically active body in the solar system. Then there was Europa, another Galilean moon, slightly smaller than Earth's moon, covered in a smooth surface of ice crisscrossed by long, linear, dark features that looked like cracks. The smoothness of the surface suggested it was geologically young, being continuously resurfaced. The cracks suggested that the surface was moving, that the ice shell was in motion, The implication, not confirmed until later missions, but strongly suggested by Voyager's data, was that beneath Europa's ice shell lay a liquid water ocean, maintained liquid by tidal heating from Jupiter's gravity, shielded from the radiation-blasted surface by the ice above it. A global subsurface ocean on a moon of Jupiter. This was one of the most profound implications of the Voyager mission. Not just that one moon was surprisingly interesting, but that the solar system was far more complex, far more diverse, far more potentially hospitable to life in unexpected places than anyone had imagined. Voyager 1 also discovered Jupiter's ring system, a faint, thin ring of particles orbiting Jupiter's equator, previously unknown. Saturn was known to have rings. Jupiter was not. The rings were so faint that they could only be seen in Voyager's images when the spacecraft was looking back toward the Sun after its closest approach, when the geometry was right for the dust particles in the rings to scatter sunlight toward the cameras. Voyager 1's Jupiter encounter lasted months from first detection to last image. By the time it moved on, it had returned over 18,000 images of Jupiter and its moons, discovered active volcanoes on Io, provided strong evidence for a subsurface ocean on Europa, discovered Jupiter's rings, measured the detailed structure of Jupiter's atmosphere, and fundamentally transformed our understanding of the outer solar system. And it was still only at Jupiter. Still had Saturn ahead. Voyager 1 reached Saturn on November 12, 1980, 3 years and 2 months after its launch. Its trajectory had been carefully designed to allow a close flyby of Saturn's largest moon, Titan, which was considered a high scientific priority because Titan was known to have a thick atmosphere, the only moon in the solar system with one, and was believed to potentially harbor conditions interesting for astrobiology. That Titan flyby would determine Voyager 1's subsequent trajectory. A close approach to Titan required a path that would fling Voyager 1 out of the plane of the solar system, up and away from the ecliptic, the flat disk in which the planets orbit. This meant that after Saturn, Voyager 1 would not be in a position to visit Uranus or Neptune. Those worlds would be left to Voyager 2. But the Saturn encounter itself was extraordinary. Saturn's rings, visible from Earth for centuries, observed by Galileo with enough puzzlement that he thought Saturn might be a triple planet, were revealed by Voyager 1 in stunning detail. The rings, which from Earth appear as a few broad bands, turned out to be composed of thousands of individual ringlets, a complex structure of remarkable intricacy. The gaps in the rings, including the famous Cassini division, a dark gap visible from Earth, were found to be not empty, but filled with sparse ring material. The rings were sculpted by the gravitational influence of small moons, shepherd moons, that orbit within and near the rings and gravitationally confine the ring particles into their observed structures. The rings were also found to contain structures that defied simple explanation. Spokes, dark radial features that appeared and disappeared over the timescale of hours, were seen crossing the rings. They were later understood to be caused by electromagnetic effects, charged dust particles being levitated above the ring plane by Jupiter's magnetic field. But at the time of Voyager's flyby, they were completely unexpected and baffling. Saturn's atmosphere, like Jupiter's, was revealed to have complex banded structure and storm systems, though Saturn's colors are more muted. Cream and tan rather than Jupiter's vivid oranges and browns, because Saturn's upper atmosphere contains a thick haze that mutes the color contrasts below. Saturn's magnetic field was revealed to be aligned almost perfectly with the planet's rotational axis, unusual among planets, whose magnetic fields are typically tilted relative to their rotation. This alignment had implications for theories of how planetary magnetic fields are generated. And then there was Titan. Voyager 1 made its closest approach to Titan at just 4,000 kilometers from the Moon's surface, closer than any other flyby target. The cameras, unfortunately, could not see the surface. Titan's thick orange-brown haze layer, composed primarily of complex organic molecules called tholins, formed by photochemical reactions in the upper atmosphere, completely obscured the surface from Voyager's visible light cameras. But other instruments told a remarkable story. Titan's atmosphere was found to be primarily nitrogen, like Earth's, unlike any other planetary atmosphere in the solar system, with methane as the second most abundant constituent. The surface pressure was about 1.5 times Earth's atmospheric pressure at sea level. The temperature was about minus 179 degrees Celsius. At that temperature, methane can exist as a gas in the atmosphere, as a liquid on the surface, and as ice, the same three phases that water occupies on Earth. Titan might have methane rain, methane rivers, methane lakes. The discovery of Titan's thick nitrogen atmosphere and complex organic chemistry transformed it from a curiosity into one of the most scientifically important objects in the solar system. It became a primary target for future missions. 24 years after Voyager 1's flyby, the Cassini-Huygens mission would arrive at Saturn, and the Huygens probe would descend through Titan's atmosphere and land on its surface. The first landing ever accomplished in the outer solar system, revealing a world of ice plains, pebbles, and evidence of flowing liquid in a landscape that looked eerily similar to Earth's. After Saturn, Voyager 1's trajectory was set. It would continue outward, not toward Uranus and Neptune, but at an angle up out of the solar system's plane, toward the boundary between the Sun's domain and interstellar space. The planetary encounters were over. The long journey into the dark had begun. On February 14th, 1990, as Voyager 1 was crossing the outer solar system, 6 billion kilometers from the Sun, Carl Sagan persuaded NASA to do something that had not been planned as part of the scientific mission. Turn the cameras around. Voyager 1's cameras were no longer being used for scientific imaging. The spacecraft was in the void between the planets and the heliopause, far from any significant object worth imaging. The cameras were scheduled to be turned off soon to conserve power for the instruments that would be used to study the interstellar environment. Sagan argued for one final act. Point to the cameras back at the inner solar system. Photograph the family of planets from which Voyager had come. Take a farewell picture of home. The result was what became known as the family portrait, a series of images of the planets of the solar system taken from outside. And within that mosaic, one image in particular became one of the most famous photographs in human history. In the photograph, there is a streak of light, a sunbeam, scattered by the optics of Voyager's camera. And within that streak, barely visible, a pale blue dot, a point of light so small that it almost doesn't register. It is Earth. Everything you have ever known. Everyone you have ever loved or will ever love. Every human being who has ever lived. Every city ever built. Every war ever fought. Every book ever written. Every piece of music ever composed. Every act of heroism and cruelty and love and indifference in the entire history of the human species. A single pale blue dot, suspended in a sunbeam in the vast darkness of space. Carl Sagan wrote about this image words that have been read millions of times since, but that bear repeating because they have not lost their power. He wrote about how our planet is a lonely speck in the great enveloping cosmic dark. About how there is no hint in the image that help will come from elsewhere to save us from ourselves. About how Earth is the only world known to harbor life. About how the Earth is a very small stage in a vast cosmic arena. He wrote that the photograph underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. The pale blue dot photograph was not taken with sophisticated technology. It was not the product of the most powerful instruments available. It was taken with a camera designed in the early 1970s. From a spacecraft that had been traveling for 13 years, looking back at a planet that appeared smaller than a single pixel. Its power is not technical. It is philosophical. It is what happens when you change the perspective from which you view something familiar. From the surface of the Earth, our planet seems vast. Continents, oceans, mountains, the full sweep of geography and geology and weather. From 6 billion kilometers away, it fits inside a particle of scattered light. The pale blue dot is perhaps the most important thing the Voyager mission produced. Not because it advanced science, it didn't really, but because it changed how we see ourselves. And that is harder to accomplish and more lasting in its effects than any measurement. After Saturn and after the pale blue dot, Voyager 1 entered a phase of its mission with no dramatic encounters, no planetary flybys, no astonishing images. Just the long cruise through the outer solar system, across the Kuiper belt, through the termination shock, across the heliosheath, toward the heliopause. This phase of the mission lasted decades, and it produced science of extraordinary value, even if it couldn't compete visually with the images of Io's volcanoes or Saturn's rings. Voyager 1 continued to measure the properties of the interplanetary medium, the solar wind, the magnetic field carried by the solar wind, the abundance of various particles and radiation as the spacecraft moved outward. These measurements, taken continuously over decades at distances no previous instrument had reached, built up a detailed picture of how the sun's influence extends through the solar system and eventually gives way to interstellar space. The solar wind is a continuous stream of charged particles, primarily protons and electrons, flowing outward from the sun in all directions at speeds of hundreds to over 1,000 kilometers per second. It carries with it the sun's magnetic field, stretched out into a vast structure called the heliosphere, the bubble of solar influence that surrounds the entire solar system. As the solar wind moves outward, it eventually encounters the interstellar medium, the gas and magnetic field that fills the space between stars. The boundary where the solar wind slows to subsonic speeds is called the termination shock. Beyond that lies the heliosheath, a region of compressed, turbulent solar wind material. And beyond the heliosheath is the heliopause, the actual boundary between the Sun's domain and true interstellar space. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the Sun, 94 times the distance from the Earth to the Sun. The crossing was detected through changes in the behavior of the solar wind particles measured by Voyager's instruments. The solar wind slowed, the particles became denser and hotter, and the magnetic field changed character. Voyager was in the heliosheath. Then came the longer wait. Voyager 1 crossed the heliosheath, traveling through the turbulent, compressed solar wind in this region. For the next several years, the science team expected the heliopause to have certain characteristics that as Voyager crossed it, the solar wind particles would disappear and be replaced by interstellar particles, and that the magnetic field direction would change significantly. What actually happened was more complicated and more interesting. The crossing of the heliopause, the entry into true interstellar space, was one of the most anticipated events in the history of planetary science. Scientists had been waiting for it since the late 1970s. When it finally happened, it didn't happen the way anyone expected. In the summer of 2012, the high-energy particle instruments on Voyager 1 detected a dramatic change. The count rate of particles coming from inside the solar system, lower energy particles associated with the solar wind, plummeted. Simultaneously, the count rate of cosmic rays, high-energy particles coming from interstellar space, accelerated by distant supernovae and other energetic events, jumped dramatically. This was the signature of crossing into interstellar space. The solar wind particles were being excluded by the heliopause. The cosmic rays were flooding in, no longer shielded by the solar wind's magnetic field. The particle data was clear, but the magnetic field data was puzzling. The direction of the magnetic field hadn't changed the way scientists expected. Inside the heliosphere, the Sun's magnetic field is carried outward by the solar wind and twisted by the Sun's rotation into a spiral pattern, the Parker spiral. Scientists expected that crossing the heliopause would reveal a clear change in magnetic field direction as they entered the interstellar magnetic field. The magnetic field direction didn't change significantly. It changed in strength and character, but remained roughly in the same direction. This led to extended debate in the scientific community about whether Voyager had actually crossed the heliopause or had entered some intermediate region not predicted by models. Eventually, in September 2013, NASA officially announced that Voyager 1 had entered interstellar space based on analysis of a solar energetic particle event in April 2013 that caused oscillations in the plasma around Voyager, allowing scientists to measure the plasma density. The density matched predictions for the interstellar medium. Voyager 1 had left the solar system. The first time in history that a human-made object had crossed the boundary between the Sun's domain and the space between the stars. The distance at which this crossing occurred was approximately 121 astronomical units from the Sun, about 18 billion kilometers. At that distance, the light travel time between Earth and Voyager was approximately 16.9 hours. a signal sent from JPL to Voyager took nearly 17 hours to arrive. A question and answer would take over 33 hours. Communication with the most distant human-made object requires patience. What did interstellar space look like to Voyager's instruments? Not dramatically different from what it had been in the outer Helios sheath. There is no sharp visual boundary, no visible change in the environment. The changes were in the particle populations and the plasma density, detectable by instruments but not visible to any camera. The heliopause, up close, is not a sharp wall, but a gradual transition, somewhat more abrupt than expected, but still spread over a region of uncertain extent. What Voyager measured in the interstellar medium, the first direct measurements ever taken in this environment, has been extraordinarily valuable. The density of the interstellar plasma, the temperature of the interstellar electrons, the strength and orientation of the local interstellar magnetic field. Properties that were previously inferred from remote observations and theoretical models could now be measured directly. And some of the measurements matched the models. Others were surprising and have required revisions to our understanding of the interstellar environment. Voyager 1 is still functioning, still sending data. As of the time of this writing, it is more than 23 billion kilometers from the Sun, approximately 155 astronomical units. Its radio signals traveling at the speed of light take more than 22 hours to reach Earth. The spacecraft is moving at approximately 17 kilometers per second relative to the Sun, about 61,000 kilometers per hour, or roughly 524 million kilometers per year. It is the most distant human-made object in existence, and it is still alive. One of the most remarkable aspects of the Voyager mission is that the spacecraft are still operating after nearly 50 years. This was not expected. The design lifetime of the Voyager spacecraft was 5 years, enough to complete the planetary encounters and conduct some science in the outer solar system. Nearly 50 years later, Voyager 1 is still transmitting, still collecting data, still functioning in an environment its designers never imagined it would reach. How is this possible? The power system is the key constraint. Voyager's 3 radioisotope thermoelectric generators, RTGs, convert the heat from the radioactive decay of plutonium-238 into electricity. Plutonium-238 has a half-life of 87.7 years, meaning that roughly every 88 years, half of the remaining plutonium decays and the power output halves. After nearly 50 years, approximately 30% of the original plutonium has decayed, and the power output has fallen to roughly 40% of the original level, from about 470 watts at launch to around 290 watts today. To conserve power, instruments have been turned off one by one over the decades. The imaging system, the cameras, was turned off in 1990 after the family portrait images were taken. Various scientific instruments have been shut down as power became too scarce to run them all. The mission team at JPL has carefully managed the remaining instruments to maximize scientific return within the available power budget. But the clock is ticking. By roughly 2025, power levels will fall below the threshold needed to operate any scientific instruments. One by one, the remaining instruments will be shut down. Eventually, the spacecraft will not have enough power to transmit data back to Earth. At that point, The mission, in any scientific sense, will be over. But Voyager 1 will continue to travel. Long after its transmitter has gone silent, long after its instruments have powered down, long after JPL has lost the ability to communicate with it, Voyager 1 will continue on its trajectory, moving away from the Sun at 17 kilometers per second, following the laws of orbital mechanics through interstellar space. The engineering team at JPL has performed remarkable feats to extend the mission. In 2017, they successfully fired Voyager 1's trajectory correction maneuver thrusters, small rocket motors that had not been used since 1980 during the Saturn flyby, to adjust the spacecraft's orientation. The thrusters worked perfectly after 37 years of dormancy. This was considered something close to a miracle by the engineers involved. Finding the original code from 1977 to run the test, verifying that the 37-year-old thruster fuel had not degraded, commanding the burn, and then waiting 17 hours for the signal confirming success. It was, by any measure, an extraordinary piece of engineering recovery. Communication with Voyager requires the Deep Space Network, a global network of large radio telescopes operated by NASA to communicate with spacecraft throughout the solar system. The antennas, the largest of which are 70 meters in diameter, must be precisely pointed at Voyager's location. Their enormous collecting areas required to gather the faint whisper of Voyager's 23-watt transmitter from a distance of billions of kilometers. In 2023, a hardware issue with Voyager 1's flight data system computer caused the spacecraft to transmit garbled data back to Earth. For several months, the science team received meaningless data from the most distant spacecraft in history. Engineers worked through the problem methodically, eventually identifying the cause, a single corrupted memory chip in one of the spacecraft's computers, and devising a workaround that shifted the code to different memory locations. The fix worked. Voyager 1 was restored to full communication. The fact that engineers in 2023 could diagnose and repair a computer problem on a spacecraft built in the 1970s, now more than 23 billion kilometers away, with a 22-hour one-way communication delay, is itself one of the most remarkable achievements in the history of engineering. Before we follow Voyager into the deep future, we need to understand fully what it changed, what we know now that we could not have known without it. Because the scientific legacy of the Voyager mission is not a list of discoveries that happened and were filed away. It's a permanent transformation of our understanding of what the solar system is. Before Voyager, the outer solar system was largely a mystery. We knew Jupiter and Saturn were gas giants. We knew they had moons. The Galilean moons of Jupiter had been known since 1610. We knew Saturn had rings. We had rough ideas about the sizes, masses, and orbital parameters of these objects. But we had no detailed knowledge of their surfaces, their atmospheres, their magnetic environments, their internal structures. After Voyager, we knew that Io was the most volcanically active body in the solar system. This was not a refinement of a previous estimate. This was the discovery of a phenomenon no one had predicted. The active volcanoes of Io were entirely unknown before Voyager 1. They were discovered in the images returned from the flyby. This discovery fundamentally changed our understanding of what geological activity requires. It can be driven by tidal heating, not just residual internal heat from formation. After Voyager, we knew that Europa almost certainly had a subsurface liquid water ocean. This was not a confirmed fact from Voyager. The confirmation required later missions. But the evidence was strong enough in Voyager's data that the scientific community took it seriously. And the implications were enormous. If liquid water can exist beneath an ice shell on a moon of Jupiter, then the habitable zone for life in the solar system is not limited to the narrow band where surface liquid water is possible. It extends to any world with sufficient internal heating, regardless of its distance from the Sun. After Voyager, we knew that Saturn's rings were incomparably more complex than their appearance from Earth had suggested. Not a few broad bands, but thousands of ringlets, sculpted by shepherd moons, containing spoke-like structures caused by electromagnetic effects, with structures at scales ranging from meters to hundreds of kilometers. The rings became one of the most studied subjects in planetary science precisely because Voyager revealed how much complexity they contained. After Voyager, we knew that Titan had a thick nitrogen atmosphere with complex organic chemistry. This made Titan not just an interesting curiosity, but a potential laboratory for studying the chemistry of the early Earth, or even a potential abode for unconventional life, based on liquid methane rather than liquid water. The discovery of Titan's atmospheric complexity directly motivated the Cassini-Huygens mission, which studied Saturn and Titan in extraordinary detail from 2004 to 2017. After Voyager, we knew about the magnetic environments of Jupiter and Saturn in detail. Their radiation belts, their magnetospheres, the complex interactions between their magnetic fields and their moons. These measurements directly influenced the design of subsequent missions and our understanding of how planetary magnetic fields interact with the solar wind. After Voyager, we knew, from its passage through the outer solar system and eventual crossing of the heliopause, the direct properties of the interstellar medium. Not inferred from remote observations, directly measured. The density of interstellar plasma, the temperature of interstellar electrons, the strength and direction of the local interstellar magnetic field. Each of these discoveries spawned decades of subsequent research. Each led to new questions, new missions, new theoretical frameworks. The history of outer solar system exploration, Galileo at Jupiter, Cassini at Saturn, New Horizons at Pluto, Juno at Jupiter, the Europa Clipper, is a direct consequence of what Voyager started. Every subsequent mission was designed, in part, to follow up on questions Voyager raised. The Voyager mission is often described as the greatest scientific reconnaissance mission in history. That's a defensible claim. In terms of the ratio of scientific return to mission cost, in terms of the number of new phenomena discovered per mission, in terms of the lasting transformation of an entire field, outer solar system planetary science, Voyager has few competitors. And it was done with 1970s technology, with a computer smaller than a modern pocket calculator, with cameras designed from television technology, with a 23-watt radio transmitter, with a team of engineers and scientists who had no GPS, no internet, no powerful computing for trajectory simulation, who had to work out many of the gravitational assist calculations essentially from scratch, using mathematical techniques that were new at the time. The Voyager mission is a monument to what human ingenuity can accomplish when it is given a clear goal, sufficient resources, and enough time. Now we reach the part of tonight that goes beyond what has already happened. Beyond the planetary encounters, beyond the crossing of the heliopause, beyond the current mission. We're going to follow Voyager 1 into the future, far into the future. And what we find there is humbling. First, let's establish the scale of the problem. Voyager 1 is currently moving at approximately 17 kilometers per second relative to the Sun. In 1 year, it travels approximately 536 million kilometers. In 10 years, about 5,36 biljoonaa kilometriä. In 100 years, about 53,6 biljoonaa kilometriä. In 200 years, about 536 biljoonaa kilometriä. The nearest star to our Sun, Proxima Centauri, is approximately 40 trillion kilometers away. At Voyager 1's current speed, it would take approximately 74,000 years to reach the distance of Proxima Centauri. But Voyager 1 is not aimed at Proxima Centauri. It's heading in a different direction, toward the constellation Ophiuchus. The star it's heading most directly toward is called AC plus 793888, also known as Gliese 445, a red dwarf star about 17.6 light-years away. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of this star. 1.6 light-years is still a vast distance. The distance light travels in 1.6 years, or about 15 trillion kilometers. That's close in galactic terms. Gliese 445 would, for a period around that time, be the closest star to our solar system, slightly closer than Proxima Centauri. But in practical terms, 1.6 light-years is still an enormous gulf. Voyager 1 will not enter the planetary system of Gliese 445, if it has one. It will pass by at a distance equivalent to roughly 400 times the distance from the Sun to Pluto. In 10,000 years, Voyager 1 will be approximately 170 light-years from the Sun. It will be deep in interstellar space, surrounded by the gas and dust of the Orion arm of the Milky Way. The Sun will be a relatively bright star, perhaps magnitude -1 to 0, similar to Sirius as seen from Earth. Visible, but not overwhelmingly so. Over these 10,000 years, the spacecraft will change very little. The radioactive decay of the plutonium will continue, generating progressively less heat. The temperatures on the spacecraft will drop as the RTGs cool and as the spacecraft moves farther from the Sun. The electronic components, the computers, the instruments, will be long dead, their last transmissions already sent. But the physical structure of the spacecraft, the aluminum bus, the gold-plated copper disc, the titanium framework, the antenna, will be largely intact. Metal doesn't corrode in the vacuum of interstellar space. There is no oxygen, no water, no weathering. A metal structure in interstellar space can persist for billions of years. The primary threat to Voyager over these timescales is not corrosion or weathering. Its impacts, collisions with interstellar dust particles, micrometeorites, and occasionally larger objects. At 17 kilometers per second, even a tiny dust grain carries significant kinetic energy. Over thousands of years, the surface of the spacecraft will be gradually eroded by this interstellar bombardment. The antenna will pitted. The golden record will be microcraters scarred on its exposed surface. But the basic structure will remain. In approximately 300 years, Voyager 1's power systems will have failed entirely. No more signals, no more data. The most distant human artifact will have gone silent, but it will still be moving. In approximately 300 years, the same timescale as the silence of the transmitter, Voyager 1 will reach the inner boundary of the Oort cloud. The Oort cloud is the vast, spherical shell of icy bodies that surrounds the solar system at enormous distances, from roughly 2,000 to 200,000 astronomical units from the Sun. This is the reservoir of long-period comets, objects that occasionally get gravitationally perturbed by passing stars or galactic tides, and fall into the inner solar system on orbits that bring them close to the Sun for the first time in millions of years. Halley's Comet, which completes its orbit every 75 years or so, is a short-period comet. But the most distant comets we observe come from the Oort cloud, on orbits that take tens of thousands to millions of years to complete. The Oort cloud is not a solid structure. It's a vast, diffuse collection of perhaps trillions of icy objects, each one tiny by planetary standards, separated by enormous distances. The average separation between Oort cloud objects is millions of kilometers, far enough apart that Voyager 1 will almost certainly pass through the entire Oort cloud without coming within any significant distance of any individual object. The Oort cloud represents the true gravitational extent of the solar system, the region where objects are gravitationally bound to the Sun, even if only loosely. Voyager 1, traveling at escape velocity, will pass through the Oort cloud and eventually leave even these gravitationally loosely bound objects behind. The transit of the Oort cloud will take approximately 300 years to enter, and will be completed by the time Voyager has traveled for about 30,000 years total. At that point, Voyager 1 will have left the solar system in the most complete sense, past even the most distant objects bound to the Sun's gravity. Over the 100,000-year timescale, humanity, if it still exists, will have changed beyond recognition. 100,000 years ago, Homo sapiens sapiens had not yet reached Europe or the Americas. The agricultural revolution was 90,000 years in the future. All of recorded history, all of science, all of technology, all of civilization, everything we have created and thought and built, is contained within less than the last 1.5% of that 100,000-year window. What will humanity be like in 100,000 years? We cannot know. We can barely project 100 years ahead with any confidence. 100,000 years is a span across which the very nature of humanity itself might transform beyond recognition. Biological evolution, technological augmentation, the development of artificial intelligence, the colonization of other worlds. Whatever exists in 100,000 years that can trace its origin to current humanity will almost certainly not be recognizable as human in any current sense. But Voyager 1 will still be there, moving at 17 kilometers per second, silent, dark, intact, the most persistent artifact of what we are now. In 1 million years, Voyager 1 will be approximately 17 light-years from the Sun. Still in our galactic neighborhood, the Orion arm of the Milky Way, but now a significant distance from its origin point. At this distance, the Sun will be invisible to the naked eye. too dim to see without optical aid. Voyager 1 will be surrounded by stars, the stars of the Orion Arm, each one separated from its neighbors by several light years. But the Sun will be indistinguishable from any of them by brightness. Voyager will be, in the most literal sense, lost among the stars. But here's something important that most people don't realize. Over 1 million years, the stars themselves move. The Sun moves relative to its neighboring stars, orbiting the galactic center at approximately 230 kilometers per second. The other stars also orbit the galactic center, each at slightly different speeds and in slightly different orbits. Over 1 million years, the relative positions of the stars change significantly. The pulsar map on the Golden Record, designed to allow any finder to identify the Sun's position by triangulating from the known locations and periods of 14 pulsars, will need updating. Pulsars slow down over time as they radiate away their rotational energy. In 1 million years, the periods of the pulsars on the map will have changed enough that a finder using them would get the wrong answer. In 10 million years, some of the pulsars will have slowed to the point of invisibility. The stellar neighborhood through which Voyager 1 travels will also change. Stars that are currently far from Voyager's path may have moved close enough to be encountered in 1 million years. Stars currently nearby may have moved away. The three-dimensional map of the stellar neighborhood is not static. It's constantly shifting, with stars drifting relative to each other at tens of kilometers per second. 1 million years is also long enough for significant evolutionary change in biology. In 1 million years, a species can become unrecognizable from its ancestor. Homo erectus, our ancestor from 1 million years ago, was substantially different from us. Smaller-brained, different in skeletal structure, without language in any form we would recognize. 1 million years from now, whatever evolves from us will be as different from us as we are from Homo erectus, or more so, given the likely acceleration of change from technology. Whatever exists on Earth in 1 million years, if anything exists, if Earth is still habitable, if consciousness has survived in some form, will be so different from us that calling it humanity would be a stretch of the term. And yet Voyager 1 will still be there, still moving, still carrying the Golden Record, still the farthest traveled artifact of whatever we are right now. In 10 million years, Voyager 1 will be approximately 170 light-years from the Sun. It will have passed through or near the vicinities of perhaps a handful of star systems. Never close enough to be gravitationally captured, never close enough to be detected by any instrument we can currently imagine, but passing through the general neighborhoods of stellar systems in ways that would be dramatic on a map of the galaxy. 10 million years is the timescale of continental drift. 10 million years ago, the Himalayas were not yet at their current height. The Sahara alternated between grassland and desert on timescales of thousands of years, but in the longer term looked broadly similar to today. The split between the lineages that would become humans and chimpanzees had just occurred. Our most recent common ancestor with chimps lived approximately 6 to 7 million years ago. Over 10 million years, species arise and go extinct. Ecosystems assemble and collapse. The continents drift measurably. Plate tectonics moves continents at a few centimeters per year, which amounts to hundreds of kilometers over 10 million years. The Atlantic Ocean will be measurably wider. The Red Sea will be larger as Africa splits from the Middle East. the topography of the planet will be different. And yet, Voyager 1 will still be moving through interstellar space at 17 kilometers per second, undisturbed, unchanged in any fundamental way. The spacecraft itself is far more durable than any biological or geological feature of the planet that built it. At 10 million years, Voyager will have encountered no stars closely enough for a gravitational interaction. The average distance between stars in the Milky Way is several light years, and Voyager's trajectory does not aim it at any star. It wanders through the stellar neighborhood on a path determined by its launch conditions and any gravitational encounters along the way. But those encounters, from the weak gravity of widely separated stars, produce only slow, gradual changes in trajectory over millions of years. The golden record, by 10 million years, will show significant surface cratering from micrometeorite impacts. Tiny dust grains and particles of interstellar matter that have struck the disk's surface over millions of years at high relative velocity. The information on the record, the images, the greetings, the music, is encoded in the physical structure of the grooves. Surface cratering will have degraded the outermost grooves, but the inner grooves, which encode the bulk of the information, will still be largely intact. The record will still be, in principle, playable. Now we reach the truly vast timescale. 1 billion years. In 1 billion years, Voyager 1 will be approximately 17,000 light-years from the Sun. It will have moved from the Orion arm of the Milky Way, our current home, into other regions of the galactic disk. The galactic structure itself will have changed, not beyond recognition, but measurably. The spiral arms will have rotated. The distribution of stars in the solar neighborhood will be completely different. 1 billion years from now, the Sun will itself be nearing the end of its main sequence life. As we discussed in a previous episode, the Sun is approximately 4.6 billion years old and has about 5 billion years left on the main sequence before it begins expanding into a red giant. In 1 billion years, the Sun will be noticeably brighter than today, perhaps 10% more luminous. And the Earth, if it still exists, will be experiencing conditions approaching the threshold of the runaway greenhouse effect. 1 billion years is also the timescale on which the galaxy itself undergoes significant change. The Milky Way's ongoing merger with the Andromeda galaxy, currently 2.5 million light-years away and approaching at about 110 kilometers per second, will be well underway in 1 billion years. The merger is expected to be largely complete by about 4 to 5 billion years from now. But the outer regions of the two galaxies may begin to interact gravitationally in the next few billion years. On the 1 billion year timescale, stars live and die. A star of the Sun's mass has a total lifetime of about 10 billion years. In 1 billion years, all stars that were somewhat more massive than the Sun when Voyager launched will have died, burned through their fuel, expanded into giants, shed their outer layers, become white dwarfs. The stellar neighborhood of Voyager travels through in 1 billion years will be populated by different stars than exist today. Some the same, some new stars that have formed from interstellar material since our time. What about the spacecraft itself? At 1 billion years, what remains? The fundamental structure of Voyager, its aluminum frame, its titanium components, its gold-plated copper disk, will be substantially intact. Metal does not corrode in the vacuum of space. There is no oxygen, no water, no weathering. The primary degradation mechanism is the continued bombardment by interstellar particles, micrometeorites, cosmic ray protons, interstellar dust. Over 1 billion years, the surface of the spacecraft will be eroded. The golden record surface will be significantly cratered, the outermost information layers degraded. The aluminum structure will have absorbed cosmic ray impacts over 1 billion years, producing damage at the atomic level through a process called displacement damage. Cosmic ray protons striking aluminum nuclei and knocking them out of their lattice positions. But the fundamental objects will still be there. The mass will still be there. The general shape will still be recognizable. Voyager 1, or what remains of it, will still be a coherent object moving through interstellar space in 1 billion years. Not functional, not communicating, not carrying legible information on its golden record. But there, persistent, an artifact. This is one of the most profound things about the Voyager mission, and about what it means to send an object into space. In the vacuum of interstellar space, matter is extraordinarily persistent. The things we build persist far longer in space than they do on Earth, where weathering, oxidation, biological activity, geological processes, and human activity continuously transform and destroy the material record of the past. In space, there is no such transformation. An object placed in interstellar space is, in the deepest physical sense, permanent. On timescales that exceed the entire history of life on Earth. We've followed Voyager 1 from its launch in September 1977 through its encounters with Jupiter and Saturn, through the pale blue dot photograph, through the crossing of the heliopause and entry into interstellar space, to its current position more than 23 billion kilometers from the Sun, and then forward through 10,000 years and 100,000 years and 1 million and 10 million and 1 billion years, to its ultimate fate as an imperishable artifact drifting through the Milky Way for as long as the galaxy exists. What does all of this mean? It means, first, that we are a species capable of extraordinary feats of engineering, patience, and foresight. The Voyager mission was conceived in an era of slide rules and punch cards, executed with computing power 1 million times less than a modern smartphone. And it worked. For nearly 5 decades. Across distances no instrument had ever covered. Returning science of permanent value and images of permanent beauty. Still operating, still transmitting, still surprising its handlers with its resilience. It means, second, that we have already sent something beyond the solar system. We have already crossed the boundary between the Sun's domain and interstellar space. Not humans, not yet, not in any near future, but a piece of us. An artifact of our civilization, something that carries, in the golden record, a portrait of what we are and what we care about. Something that will outlast every human institution, every government, every language, every biological structure currently alive on Earth. It means, third, that time and space are not abstractions. When you trace Voyager 1's trajectory forward, when you follow it through 40,000 years to its closest approach to Gliese 445, through 1 million years as it becomes unreachable even by the most powerful future telescopes, through 1 billion years as it drifts through regions of the galaxy the Sun has never entered. The scale of the universe becomes visceral, in a way that no diagram and no calculation can quite achieve. We are small. We are brief. We exist on one planet, around one star, in one arm of one galaxy among trillions. Our civilization is measured in thousands of years, the universe in billions. Our technology reaches tens of billions of kilometers. The galaxy spans hundreds of thousands of light years. And yet, something we built left the solar system. Something we built is, right now, in interstellar space. Something we built will still be traveling through the galaxy when the sun has died and the Earth has been consumed. Every trace of what we currently are has long since been transformed into something unrecognizable. Voyager 1 is not immortal. Nothing is. In the far, far future, in the unimaginable depths of time, when the stars themselves have dimmed and the galaxy has changed beyond recognition, even Voyager's metal structure will eventually be degraded by the accumulated effects of cosmic radiation, dark matter interactions, and other processes we can barely calculate. On timescales of trillions of years, even the most durable matter transforms. But for all practical purposes, for any timescale relevant to life, civilization, or even the current stellar population of the Milky Way, Voyager 1 is permanent. It will outlast us. It will outlast our sun. It will outlast everything that made it. That's remarkable. And it says something important about us. Let's return at the end to the golden record. Because what we chose to put on it, what Carl Sagan and his committee chose in 1977 to represent humanity to the cosmos, tells us something profound about who we were and about who we wanted to be seen as. They chose Bach. They chose Chuck Berry. They chose whale songs and human laughter and the sound of rain. They chose photographs of a nursing mother and an athlete and a supermarket and a sunset. They chose greetings in 55 languages, including Akkadian, a language that had been dead for 2,000 years at the time of the recording. They chose to include the sounds of a heartbeat and of footsteps. They did not choose to include a nuclear weapon. They did not choose to include a photograph of a war. They did not choose to include any of the vast catalog of human violence and cruelty that had been as much a part of our history as Bach and whale songs. This was a choice. A deliberate editorial choice about how to represent humanity to a potential alien observer. Was it honest? Probably not completely. A complete portrait of humanity would include the Holocaust and the Gulag alongside Beethoven. It would include slavery alongside the wedding songs. It would include the bombing of cities alongside the sound of rain. But Carl Sagan didn't see the golden record as journalism. He saw it as aspiration, as a statement not of what we are, but of what we hope to be. A message that says, these are the things we value, even when we often fail to act in accordance with those values. These are the things we find beautiful, even when we produce ugliness. This is what we might be if we survive our adolescence as a civilization. The golden record is moving away from us at 17 kilometers per second. It will never come back. Whatever it says about us is what it will always say. Frozen in 1977, carrying that moment's best hope for what humanity is and wants to be. 47 years later, the world has changed enormously. But many of the things that went on the golden record haven't changed at all. Bach still sounds like Bach. Whale songs are still being sung in the ocean, The sound of rain on leaves is unchanged. The image of a mother nursing a child is timeless. Some things are permanent, even if we are not. And Voyager carries them outward into the dark for as long as the spacecraft lasts. Right now, at this exact moment as you watch this, Voyager 1 is out there, moving at 17 kilometers per second through the interstellar medium, slightly more than 23 billion kilometers from the Sun. Its faint radio signal, 23 watts, spreading across the volume of a sphere whose surface is now 23 billion kilometers away, is washing over Earth at this moment, arriving with a power of 10 to the minus 16 watts. A signal so faint that it requires a 70-meter antenna and the most sensitive receivers ever built to detect it. The signal is still there. The spacecraft is still transmitting. The mission, in whatever form remains to it, with whatever instruments are still operating, continues. Somewhere above us, engineers at the Jet Propulsion Laboratory in Pasadena, California, are watching the telemetry from Voyager 1, checking temperatures and power levels and instrument status, planning the next command sequence, working the problem, whatever the current problem is, with the same methodical patience that has characterized this mission for nearly 5 decades. Voyager 1 is the most distant expression of human intelligence that has ever existed. It carries our mathematics, our music, our faces, our greetings, our science, and the sound of a heartbeat. It is moving in a direction that will take it away from everything we know, forever, at a speed that will never decrease because there is nothing in interstellar space to slow it. In 10,000 years, it will be dark and silent. In 40,000 years, it will make its closest approach to another star. In 1 million years, it will be completely beyond any human knowledge of its location. In 1 billion years, it will be an artifact in a galaxy that no longer contains a sun. We sent it. We chose to do this. In 1977, with the technology of that moment, we built the best spacecraft we could build and gave it the best trajectory we could calculate and loaded it with the most carefully chosen message we could assemble and sent it into the dark. That's what we are, a species that does this. Not always, not consistently, not without enormous contradiction and failure and cruelty. But sometimes, when we're at our best, we send something into the dark with a message that says, "We were here, we were curious, we found the universe beautiful. Here is what we sounded like when we were trying." Voyager 1 carries that message. It will carry it for billions of years. Go outside tonight. Look up. You can't see Voyager 1. It's far too dim, far too small, far too distant. But you can know it's there. In the direction of the constellation Ophiuchus, moving away from us at 17 kilometers per second, carrying our music into the dark between the stars. That's enough. That has to be enough. And somehow, it is. Sleep well tonight, knowing that the loneliest object we've ever built is still out there, still moving, still carrying something of what we are into the permanent dark. Before we close completely, one final attempt to make Voyager's distance feel real. Light travels at 300,000 kilometers per second. In 1 second, light completes 7.5 laps around the Earth. In 8 minutes, it crosses the distance from the Sun to the Earth. A signal from Voyager 1 traveling at the speed of light. currently takes more than 22 hours to reach Earth. 22 hours at the speed of light. That is the distance between us and the most distant object we have ever built. If you wanted to drive to Voyager 1 in a car at highway speed, let's say 100 kilometers per hour, the journey would take approximately 26 million years. You'd need to have started driving before the Himalayas existed, before the first hominids walked the Earth, before the great apes had diverged from the lineage that would become us. And yet, Voyager is still in our galaxy, still in the same spiral arm, still within the Milky Way, a galaxy 100,000 light-years across. In the vast context of the galaxy, Voyager 1 has barely moved from the Sun. It is, in galactic terms, still practically at home. That's the scale of the problem. That's the scale of the universe. That's why the distances Voyager has traveled, as extraordinary as they are by human standards, are still only the first tiny step of an impossibly long journey. And yet, we built it. We launched it. We tracked it for nearly 50 years. We received its signals. We fixed its computers from 23 billion kilometers away. We did this with 1970s technology, with slide rules and punch cards and 23-watt radio transmitters. Imagine what we could do if we really tried. Even now, as you read this, the Voyager interstellar mission continues at JPL. A small team of scientists and engineers, fewer than a dozen dedicated to the mission at any one time, supported by periodic involvement from many others, monitors the spacecraft daily, analyzes the data it returns, plans the next phase of the mission, and works to extend the operational lifetime of the spacecraft as long as physically possible. The data Voyager is returning right now. From its instruments measuring the interstellar plasma, the magnetic field, the cosmic ray environment, the ultraviolet background, is unique. No other spacecraft is where Voyager is. No other instrument is making these measurements. Everything Voyager tells us about the interstellar environment is information we could not get any other way. The mission team knows that the clock is running. Every year, Voyager's power output decreases slightly. Every year, the margin between what the spacecraft can power and what it needs to power its remaining instruments gets thinner. Decisions have already been made to shut down heaters in some parts of the spacecraft, risking the failure of components that cannot function in the extreme cold of interstellar space. In order to keep the most scientifically valuable instruments running a little longer. It's a kind of triage, a constant, careful management of an aging, fragile system across a distance that makes every decision slow and every failure potentially irreversible. A 22-hour light travel time means that if something goes wrong, you know about it 22 hours after it happened, and any command you send to address it won't arrive for another 22 hours. The mission team operates in a universe where the speed of light itself is a constraint on their ability to respond. And yet, they persist. Every day. Monitoring, planning, preserving. There's something deeply human about this. The commitment to maintaining contact with something so far away, for so long, for science, that is by necessity slow and incremental. The refusal to give up on a spacecraft that has already lasted 10 times its design lifetime. The ingenuity applied to problems, like the 2023 computer failure, that no one could have anticipated and that have no precedent in the history of spaceflight. The Voyager mission will end. The transmitters will go silent. the last signal will be received, decoded, archived, and then there will be nothing. Just the knowledge that the spacecraft is still out there, still moving, unreachable and unseen. When that day comes, it will be the end of an era. Not just the end of a mission, but the end of direct contact with the most distant object humanity has ever created. After that, Voyager will belong entirely to the future, to the billion-year timescale, to whoever or whatever might eventually find it, to the long, silent journey through the Milky Way. Until that day, it's ours. We built it. We launched it. We've talked to it for nearly 50 years, and it has answered faithfully, with data and images and measurements that have permanently changed our understanding of the universe. That relationship between a civilization and the most distant artifact it has ever created is something worth honoring, worth understanding, worth telling. That's what tonight was for.